Another special type of uniform circular motion we need to take a look at is vertical circles. So objects moving in a circle at a constant speed in a vertical plane. For example, we have like a Ferris wheel. So let's say we have a Ferris wheel with the coordinate system here, positive x to the right and a positive y upwards. So that way it's in a vertical plane. And in vertical circles, there's two particular areas that we're most interested in. This will be the very bottom of the vertical circle and the very top of the vertical circle. So let's say that this is a Ferris wheel and we have a person sitting in the seat in the Ferris wheel here. So here's our person there. And because the Ferris wheel is going on a circle, we'll say it's going in a counterclockwise circle like this. We know that we have to have some acceleration towards the center, right? A centripetal acceleration. So this will always be towards the center, right? Even if I were to take a snapshot over here, our acceleration would be in this direction. And at the top, our centripetal acceleration will be straight down, and at the bottom, our centripetal acceleration will be straight upwards. So these will be our centripetal accelerations. So let's see how this circular motion and the centripetal acceleration that goes with it affects our free body diagrams. So let's free body diagram the person. Let's start by free body diagramming the person at the top. So all the forces acting on them, and let's use the same coordinate system we have over here. The forces acting on this person, there would be a weight going down, and there would be a normal force that the seat exerts onto the person up like this. And we'll ignore any forces in the horizontal direction. There may not be any at all. And we know the results of these forces must be an acceleration which is towards the center, and since we're at the top, the center is located directly straight down. And so then we would have, just doing this summation of forces, sum of forces in the y direction would be mass times acceleration in the y direction, which is going to be mass times, since we have a downwards arrow for our centripetal acceleration, mass times negative AC. And so what we get here is the normal force minus the weight will be equal to negative MAC, or the normal force is equal to the weight minus MAC, or the normal force is equal to the mass times gravity minus the centripetal acceleration, just factoring out the mass there. So you see that the normal force is reduced. This is actually at the top. So a lot of times we'll say normal force at the top is mass times gravity minus centripetal acceleration, or I could say this is mass times gravity minus v squared over r, or this is mass times gravity minus 4 pi squared r over t squared. All of these are centripetal accelerations, right? So the normal force at the top are these. So we can see that the normal force that the seat exerts on us at the top is less than our weight, basically. If we make it such that our centripetal acceleration were equal to g, then the normal force at the top would be mass times g minus g, which would be 0, and we would feel weightless. So if we're going in a fast enough Ferris wheel, such that v squared over r is equal to 9.8, then we would feel weightless at the top momentarily, that's why faster rides are more exciting. We feel weightless and things like that. If we flip this around, the normal force for the bottom, really the only difference, instead of rederiving the whole thing here, the only difference in our free body diagram at the bottom is that the centripetal acceleration would be acting upwards, right? And so then this becomes a positive AC. So we'd have a positive here and a positive here. And so then, using the same derivation, we have the normal force at the bottom would be equal to m times g plus AC, or m times g plus v squared over r, or m times g plus 4 pi squared r over t squared. So this is our normal force at the bottom there. And so we can see that if we were going fast enough such that the centripetal acceleration were 9.8, we'd feel weightless at the top, and we'd feel the normal force would be m times g plus g, so we'd feel twice as heavy at the bottom if the centripetal acceleration were equal to g. So this is why we feel heavier at the bottom and lighter at the top. And we need to be going, it needs to be a fairly fast Ferris wheel to really notice this a whole lot, but this is what we have. And this is really the same formulation as, remember when we had elevators and we were looking at the normal force in the elevator? We had we had the normal force from the floor onto us, we had a weight going down, and we had two different scenarios we looked at. Either we were accelerating upwards or we were accelerating downwards. And really this is exactly the same thing. The normal force at the bottom would be an upwards acceleration. The normal force at the top would be our downwards acceleration. So we've actually seen this formulation before in elevators. So this is what we have. And it doesn't have to necessarily just be like a Ferris wheel. We can also have maybe a rock at the end of a string, in which case we have tension pulling down like this and tension pulling up like that, and the tension at the top, this is going to be m times g minus AC, and the tension at the bottom, this is going to be m times g plus AC. And you kind of can conceptually think of this as that, well, in order to stay going in a circle, it must be accelerated downwards, right? In order to stay in the circle. At the top, gravity is helping this acceleration. Gravity is already in the direction of the centripetal acceleration, so I don't need quite so much tension to pull it downwards. At the bottom, though, gravity is pulling downwards, yet I need to accelerate upwards. So I'm going to need a greater tension at the bottom to pull it upwards. So if you have like a rock at the end of a string, you're swinging in a vertical circle, the place that it's going to break most likely would be at the bottom of the circle, because that's where your tension would be the greatest. We can go a step further on this, and actually let's say that we have this roller coaster here, and we're designing a roller coaster that's going to be really exciting, where the passengers don't have to be strapped into it. So you're riding this roller coaster and you don't need a seatbelt because it's designed such that you're guaranteed to not fall out. So let's see here. So let's take a look. If you're in this roller coaster here, or actually maybe we'll simplify this down a little bit. Let's just say we have, here on a roller coaster, you're like this and you're upside down. So here's your head and your arms. So here you are like that. And the forces, so let's actually free body diagram the top. And coordinate system like this. Then the forces that act on you at the top, there's going to be a normal force, and that would actually be pushing down, right? Because the normal force has to be from the surface onto you. And so this is, by the way, this is the free body diagram of you, or the person. So the normal force must push down, and also we have a weight acting down here, and we're at the top of a circle, so we have an acceleration, which is also downwards like this, and it's a centripetal acceleration. So we have, just summing this up, and actually let me flip these around. Let me flip my coordinate system around, because everything is acting downwards, so it doesn't make sense for me to call upwards positive. I'll call downwards positive. So then we have the normal force plus the weight would be equal to MAC. So then the normal force is going to be equal to MAC minus mg, or this is equal to mass times v squared over r minus g. That would be our normal force. And at the very top of this, and this is, this is very similar to what we had up here, but because our normal forces go in the opposite direction, we get this. These are flipped around here. If you get a negative answer in free body diagrams, it just means you drew the force the wrong way. So we could have actually used this formulation up here at the top, and we would have got a negative normal force, and it would have still worked out. We would just flip the direction of that force. So the normal force at the top looks like this. And if we want to ensure that the person is still in the roller coaster, then we want to make sure that normal force is at least, at a minimum, it's equal to 0. It can't be possible that our normal force is going to pull up. And since we're not strapped in, we have no other force to pull up. Right? So the normal force must be greater than or equal to 0. That's what we must have. I need to ensure there's something kind of pushing down there to keep it going in a circle. So if the normal force is greater than or equal to 0, and the normal force is this, that means that m times v squared over r minus g must be greater than or equal to 0. And clearly the mass is greater than 0, so that's not something we're interested in. So this means that v squared over r minus g is greater than or equal to 0. Or then solving this, we can say that v, just solving this whole thing, is greater than or equal to the square root of rg. So what this means is that, so we solve this for how fast we need to go in order for there to still be a normal force. The speed must be greater than or equal to the radius times the acceleration due to gravity in order for there still to be a normal force. So we say this is the minimum speed at the top. V minimum at the top of the roller coaster ride would be equal to the square root of rg. Otherwise, the acceleration due to gravity is too great and the person falls out. So this is the minimum speed needed to actually make it through a vertical circle without having to be strapped in there or anything.